Today I'm going to talk about programming, what it is and how to teach it. I'm starting with this photograph because it shows nearly everything I want to talk about. It has former US President Barack Obama helping students learn to code and probably learning himself. It shows youth learning to code and more importantly it shows youth actually enjoying learning to code and probably enjoying it because they're being successful at it. So I'm going to talk about some of the barriers to achieving more moments like this at scale across the world. I'm going to talk about the computing education and research community that's working to make moments like this possible. And I'm going to talk about my lab's research on learning programming, which are removing some of the barriers to successful learning. So like you, I love programming, and I'm guessing most of you feel similarly than I do. And I've spent a lot of time in my career, almost 20 years of research, on how to make programming easier to do. This is mostly involved inventing interactive tools like debugging tools and new forms of spreadsheet and type checking, but also studying software engineering and some of the barriers to making software as teams in organizations. And then something changed. When I became a co-founder and CTO of my software startup, I really observed something pretty concretely. I learned that tools really amplify productivity, but they don't cause it. This is a picture of my startup, AnswerDash, in 2013, and every day I observed that engineers who lacked skills, that had great tools, still produced bad code. And really skilled engineers that had bad tools still produced great code. It wasn't really a factor of whether or not they had some great technology, it was more a factor of what they knew and what they could do. It was skills that were causing productivity, and more importantly, skills that somebody had been taught or that they had learned independently. And so I want to talk about why the world is failing to educate great programmers by giving them these skills. I'm going to talk about the field of computing education research and how it's trying to solve some of these problems, and then I'll present some of my lab's research on what programming is and how to effectively teach a subset of things in programming, including programming languages, APIs, and problem solving. All right, so when I talk about teaching programming, you're probably thinking of contexts like this. A standard higher education lecture hall, sage on the stage talking about programming, and that's a reasonable thing to think of. We are all college faculty. There's a lot of college classrooms where people are learning to code. In fact, there's really more than ever. By some estimates, there's about 100,000 computer science majors globally, and of course, we all know that this is growing. But what I want to point out is that this is not just about computer science in higher education. It's not just about colleges and universities, even. There are now 25,000 coding bootcamp students. This is growing as well. Soon, it's going to have just as many students in as in higher education. But of course, it's not just about bootcamp students either. With global efforts to bring CS to everybody, especially through primary and secondary education, we already have on the order of 10 million youth around the world who are learning a little bit about computing. And if this is successful, it'll soon be something approaching a billion students if we reach all of public education across the globe. Now, that's boot camps, that's higher ed, that's school, but it's not just about school. It's also developers themselves. There are 30 million developers in the world who are learning programming languages and APIs every day. They're struggling to do that. They're learning new platforms and technologies, and sometimes their inability to learn those things is preventing them from getting their next job. And of course, it's not even just about developers at work. There's also 100 million people who are programming to support their other work, their non-software development work, and maybe their hobbies. People are going into maker spaces and learning all kinds of new skills to create new things. Even scientists who are writing programs, not with a computer science background, but with a scientific background, learning just enough programming to be able to do the data science they need to support their discoveries. Now, all of these people need computing to make progress. This is a lot of people learning to program. But it's also a really optimistic picture about this learning. I've sort of presented this as if every single person in these statistics is successfully learning, and that's just not the case. First of all, when we look at this picture, it's actually excluding a bunch of people, right? It's excluding everybody who's afraid to learn, either because they don't think they belong, or because they think that it's going to be too hard to learn. And so that's a huge barrier to all of the people who might need to do this in their work, might need to do this at school, might want to do this in school, or might want the economic security of a good paying job, but they fear it for some reason. Many also quit because the way that we teach programming is decontextualized and therefore really boring. Connecting it to people's interests really helps, but we often don't do that. Connecting it to the impact that they might have in the world can really help, but we often don't do that. Connecting it to nothing and really just teaching it as pure abstraction, pure logic, really does cause learners to leave. There's mounting evidence that shows that this is a really central reason why people quit. And then, of course, there's more nefarious reasons. Many people quit because of racism, sexism, ableism, and ageism. Some of this is explicit on the part of a teacher or a community, but a lot of it is actually not about an interpersonal interaction, but rather an institutional interaction. There are processes and policies that disadvantage particular groups. So, for example, racism might look like black students not seeing themselves represented amongst the faculty, where they don't have role models, and so they're not aspiring in that same way to pursue something. The same might be true for sexism, with women not seeing themselves represented on the faculty or experiencing sexual harassment in some systematic way. Ableism is really simple things like if you are a student who is blind and you're trying to access learning materials that are inherently and only visual, you're not going to be able to learn. And then finally, there's things like ageism, where somebody might be pursuing a career in software engineering, but companies are only recruiting from younger communities that might be in college, but not looking at older adults. And then finally, the biggest reason, and the reason I'm talking today, is that many quit just because there's poor teaching of programming. This includes poor explanations of hard concepts or no explanations at all, poor guidance or a lack of guidance altogether about how to solve problems in programming, poor feedback or a lack of feedback altogether about what somebody understands and what they don't understand and how they should practice to improve their understanding. Maybe there's even poor encouragement or an active discouragement to learn to program. For example, many teachers falsely believe in some kind of geek gene that people are born with, and they tell students that they're just not capable of learning to program after they see them fail a little bit. These are the kinds of things that constitute poor teaching and lead people to quit. Now, it's because of all of that poor teaching that actually very few people become great programmers. And so what we have left and what we tend to see in higher education computer science and bootcamp graduates are the set of people that survived all of those issues along the way. And the result is that this really small group of people, especially the ones that are really great programmers, people fight over them. There's epic battles between software companies for the greatest talent. And this leads to a lot of unemployment of developers that have weaker skills. It also probably leads to a lot of income inequality by reducing the supply of great software developers. So the big question here is, how do we educate more great programmers? And this is actually the big question that drives the field of computing education research. This is now an international community of hundreds of really outstanding researchers driving innovation in computer science teaching and learning and educational technologies. I identify as a computing education researcher. I didn't always. I pivoted about 5 years ago when I realized that skills were really the most powerful tool for shaping people's abilities in programming. So I want to start off just by explaining this field before I talk about my lab's work in this space, and I'll begin by trying to distinguish between computing education practice and computing education research. So practice, who does this? All of you probably do it. I do it. The primary and secondary teachers that have started to teach computer science do it. Stack Overflow contributors even do it when they're writing an answer online to try to help somebody solve some problem with an API or a language. Developers do it when they're at work, right? I showed you a picture of one of my engineers at AnswerDash teaching another one of my engineers. And the work that this involves is teaching classes, developing learning materials, mentoring students, assessing learning, developing academic programs for learning, right? These are all of the things that you're familiar with if you're in academia. Now, computing education research, in contrast, is a much smaller group of people. I do this, a few hundred other faculty and doctoral students do it globally. And this is really about the science of how people teach, how they learn, and how learners develop interest in computing. And this includes theories of learning and teaching, studies that try to test those theories, and innovations in teaching, whether they are educational technologies that try to scale learning, or they are teaching methods that try to improve the teaching of particularly hard concepts in a subject. And so these are really different activities, but the research really feeds into practice, just like in any other research domain. It turns out that computing education research is one of the oldest research areas in computer science. The ACM SIG-C Special Interest Group was the first ACM SIG in 1968. The largest conference on this, the ACM SIG-C Technical Symposium, was one of the first conferences in 1970. Here's a photograph of its signature charter. And up until about 2000, the CS education community really was more of a practical community. There wasn't a lot of science happening. Most of it was writing experience reports about classes that people had taught, challenges they'd faced. This has really changed, though, in the past 10 years, especially as the U.S. National Science Foundation, MacArthur Foundation, Microsoft, Google, and other companies began funding basic research in computing education. And this really coincided with a lot of the push to bring CS to everybody in public education in primary and secondary school. And so there are a lot of questions that people have started investigating. If we start from the top left, how do we effectively teach programming languages? Why do students quit computer science? Why is there so little gender and racial diversity? How can we accurately assess CS knowledge? And if we jump to the right, how can we effectively teach things like APIs? How do we motivate people to learn to code? Why are particular concepts like recursion hard to learn? So when you look at all of these questions, we actually don't have answers to most of them, and that's what researchers are trying to investigate. And yet we need those answers to be able to educate more great programmers. And then, of course, as I pointed out earlier, there's lots of different contexts in which these questions need to be answered. Some of these questions might have different answers if you're talking about primary school students who are 7 years old versus software engineers who are working in a company. And yet both might actually be learning APIs in order to create something that's driving their work or their play or their learning. So primary, secondary, college, boot camps, workplaces, and hobbies, all of these are really different contexts in which learning occur, and we need to understand them differently. Some of this work has already had a lot of impact. So here's two examples of discoveries. One is this big question of how do people develop interest in computing? Jane Margolis and many others have shown through a series of studies that interest in computing is not shaped by something that's innate. People are not born with interest in this, but by access to opportunities to develop interest. And that access is often unequal. Some people get it, some people don't. And this is really impacting policy globally. There are laws being passed in countries that are trying to ensure access to these opportunities. And then on the right, how can we lower barriers to learning to program? One of the earliest barriers that people started working on was the ability just to construct syntactically valid programs. This started way back in 1979 with the Cornell program synthesizer, and then this led to Randy Pausch's Alice in 2000, which was a drag-and-drop structured editor. This led to Mitch Resnick's Scratch at the Media Lab, which is still happening at scale, and that impacted a whole proliferation of other blocks editors. These have really eliminated syntax and type errors as a barrier to learning to program for hundreds of millions of learners because a lot of these have been deployed at scale. So this is impacting nearly everybody who's trying to learn these days. So within all of this, this is my lab. After about 5 years of working in this space, it's a pretty vibrant and large lab. I have 7 doctoral students, 5 undergraduates, and then you'll also see in this photo a large community of faculty, especially teaching track faculty in computer science, the information school, and the College of Education, who've also been supporting a lot of the work that we do. And my lab's research recently has really focused on studying effective, equitable, and scalable ways to teach hard concepts and skills in computer science, the things that I think are really the fundamental barriers to people successfully learning to program. And we've focused on trying to discover ways of teaching these hard concepts by understanding the concepts themselves. And so we've really focused on one big question first. What is programming? What are the underlying activities that it involves? Now you might think you know what programming is, right? Isn't programming a logical activity, right, of designing algorithms and data structures and trying to encode them in some formal notation and then verifying them formally, right? This is sort of the classic computer science perspective on what programming is. We sort of hide a lot of the other complexities in it, just frame it as some logical activity. And this sort of implies that all somebody needs to know is logic and a formal notation, and the rest of it is trivial. So my lab's discoveries have shown that it's not trivial, and that this definition is too narrow. It really excludes really central cognitive and social processes that are involved in that word encoding, right, and in that word designing. Both of those are actually really challenging activities that we need to explicitly teach people how to do. So one of the first foundational ideas that my lab worked on, this is work by my student Dostanay Laksa, is that programming is really a set of activities, right? You get a problem, and there's all this stuff that happens before you implement it. You interpret the problem, you search for analogous problems that might have similar solutions, you search for solutions to those problems, you verify that some solution you found might solve that problem, and only then do you might implement it and verify it to make sure that it actually addresses the problem, right? To actually do that encoding. But of course, this is also an iterative process, right? You go to some activity, you learn something, and then you return to some previous step to reevaluate the work you've done. Of course, it's not as simple as just doing these things. All of these activities require specific skills, right? Interpreting a problem requires translating some natural language statement into some more formal problem definition to help you reason about the programming problem. Or if we jump to verifying that a solution solves a problem, we have to know how to analyze algorithms, right? And understand that an algorithm is correct given some problem definition. Or verifying the implementation requires skills in testing and debugging, right? And then finally, for all of these skills, there's got to be strategies for actually approaching them, right? And there are varying strategies of varying effectiveness. And if somebody doesn't know these, they're not going to know how to approach any of these activities. Finally, programming also requires process, right? How does somebody know when to switch between activities? How do they know when to try new strategies? So if they're not monitoring their process, and monitoring their comprehension of things, monitoring the effectiveness of the strategies they've chosen, and using that knowledge, that reflection, to decide what to do next, they're also not going to be effective. So we call this self-regulation in education research. Now, the big gap here is that we teach very few of these skills in higher education and elsewhere. We maybe teach a little bit of analysis of algorithms, but only in a theory of complexity kind of way. We teach programming language syntax. We kind of teach semantics. We describe it in natural language, but we hope that people understand it. We don't really do that very rigorously. Maybe if somebody takes a software engineering class, they learn a bit about software testing. But we mostly ignore all of these other skills, even though we know now that they're really critical to successful programming. And so my lab in the past 5 years has studied 4 of these major skills. We've looked very closely at programming language syntax and semantics. We've looked at learning APIs and what that means. We've looked at these self-regulation skills that I mentioned. And then finally, 4th, we've looked at strategies for a lot of these activities and how to represent them and how to teach them. So for the rest of this talk, I'm going to go through those 4 discoveries that we have and talk about some of the studies and theories and educational technologies we've built for these, and then I'll end with implications of these discoveries for teaching, not just your teaching, but anybody's teaching at different levels. All right, let's go ahead and jump in with programming language knowledge. So most approaches to teaching programming proceed as follows, and I think you'll probably recognize this if you teach intro classes. For all of the semantics in some programming language, you might show a syntax example. You might explain the semantics of some of that syntax in natural language, and then you give somebody something to practice. You give them problems and they write programs, and you hope that they'll be able to take that knowledge of syntax and semantics and write programs. When we do it in this order, there's sort of a major oversight from our perspective and from our research, and that is that it really overlooks the importance of reading as a skill. So we're arguing that reading is really different from writing, and that writing depends on reading skills. Reading semantics are things like, how does this conditional actually execute? Whereas writing semantics is, how do I construct a syntactically valid conditional statement that does what I intend? So our argument is that these writing skills depend critically on robust reading skills, because otherwise when you write something, you won't know if it actually has the correct semantics that you want, or you might assume that it does even though it doesn't. So we've done several studies on this distinction. One of the studies that we've done recently shows that teaching reading first really does help. So we designed 2 versions of a 4-hour Python lesson, And in the control group, we did what was conventional, showing syntax, explaining semantics, and then having somebody practice writing. And in the treatment group, we had a similar sequence. We showed syntax, we explained semantics, but then before we had them practice writing, we had them practice reading to make sure that they would have a robust understanding of the semantics. And the treatment group completed more of the practice in the same amount of time. They made fewer errors in that practice, and they had a more robust understanding of those errors. So you can see a bit of the data on the right, although I won't go into it. Don't bother trying to read any of those labels. The point is that teaching reading first helped and didn't cost more time. We've also looked at how to teach some of these reading skills. In a lab experiment, we spent just 5 minutes teaching a strategy for tracing program execution. We told them, do it line by line, follow the rules of the programming language, and update a memory table to track the program state as you go. Visualize that program state. So 5 minutes of that instruction, they practiced the strategy for a little bit, and then we gave them a bunch of problems to solve. Students who used the strategy compared to students who did not scored an average of 15% higher on a post-test immediately after learning that strategy. Based on Think Aloud data, where we asked them to talk about the ways that they were reading the program, they were more systematic in doing it. And then when we later measured their performance on a course midterm that we were not responsible for, they scored an average of 7% higher on that course midterm, so almost a whole letter grade. Now, we've taken some of these insights and tried to build them into educational technologies for scale. So what we've tried to do is visualize semantics. Our theory here was that by showing semantics concretely, the cause and effect of each step of a program, that we would develop even more robust understandings of how programs execute. So this is PL Tutor on the right. It teaches JavaScript semantics by visualizing execution of one instruction at a time, linking the syntax to the side effects on control and data. So you'll see an example here in this video. This is an example of showing an if statement execute. It basically is stepping one instruction at a time, linking that to the tokens and explaining what's happening at each of these steps. So here, the expression is evaluating. It's explaining each of those steps of the expression evaluating, showing an accumulator, gathering those values, and then showing the decision that the conditional is making, and then jumping to the then branch of this. And the key thing is that learners can go back and forth. It's reverse executable. All of this state is always visible. And all of these features for all of the language constructs in JavaScript have some pretty strong effects on learning. 60% higher learning gains than a Codecademy tutorial that doesn't show this level of granularity. And PL Tutor was associated with higher midterm grades in a class that students were taking. And you might be thinking from a technical perspective, shrug, this seems really easy, it seems sort of simple. There's actually a whole bunch of hidden complexity behind making this work. We had to redesign the entire JavaScript language stack to support things like tracking the provenance of data values through history, execution history. We needed a bidirectional mapping from instructions to tokens so that we could actually highlight at the instruction level which token that mapped onto. So we had to do provenance through parsers and compilers. We needed granular execution and reverse execution so that we could go at a very low level, showing learners step by step exactly what happens in response to each part of a program executing, not by line, but by instruction. And then we needed annotated program execution histories so that we could link explanations of semantics to particular parts of the examples that we were building. So we have a whole authoring environment for this as well. So this was no small matter of engineering. We really had to re-architect a language stack. So a lot of our future work on programming language learning involves some impact and some extensions of what we've done. So we've already integrated some of these ideas into Code.org's curriculum, which is used by 10 million learners. We are building a version of the PL Tutor that models learners' knowledge as they're proceeding and then adapts itself to what a learner knows, giving them more or less practice, excluding subjects that they already know well. And this is going to allow us to go from 2 to 3 hours that they were learning, maybe down to something as short as 30 minutes or an hour, depending on their prior knowledge. We're also building tutors that don't just teach these reading skills, but also teach writing as well, and doing this online. So we're imagining that we'll be able to take a typical CS1 course that maybe takes 10 weeks and condense it down into 10 hours. We're trying to think about ecosystems of tutors for different languages. So imagine you know languages A, B, and C. We could give you an automatically personalized tutor that lets you learn language D really efficiently. So we really envision a world in which learning a programming language is the easiest part of learning to programming and not really the barrier to doing other higher level things. So that was programming language knowledge. Really big insight here is that a robust ability to read semantics is just key to the ability to write. So I want to move on now to API knowledge and distinguish between API knowledge and programming language knowledge. So most of you, when you learn APIs, you probably do a couple of things. You might read the API documentation, and you probably go and find and adapt code examples that you find online, places such as Stack Overflow. Such learning results in really brittle API knowledge, though, like where weak knowledge of an API behavior results in difficulty modifying a program, fixing it, or correctly using the API. So the question is, how do we teach robust API knowledge, and what is involved in that robust API knowledge? So my student Kyle Thayer has done some work that's found that really there's three kinds of knowledge that robust API knowledge requires. The first is something we call domain concepts. Domain concepts come from some domain in the world. They're not part of the API, but the API models them, right? And the understanding that somebody needs is both those concepts in the world and how the API models them. So here's an example. LaTeX uses the domain of typography in graphic design, but it models typography in a particular way. So like the bullets that I'm showing on the right side of this slide, there's some notion of these bullets and dashes and white space and indentation, but LaTeX has certain ways of talking about all of those. To know an API robustly, you have to know both of those concepts. And the second kind of knowledge here is parameterized code templates. These describe how to coordinate API features to achieve some range of functionality. So this bulleted list example here, you need some example that not only shows how bulleted lists work, but how you can extend them to two-tiered bulleted lists or three-tiered bulleted lists. So one example is not enough to do that. You need examples that show how an example can be modified to achieve other related behaviors. And then third, learners need execution facts about the semantics of runtime behavior. So if you think about a function call inside of some API as a black box, learners need some sort of shorthand rules that describe the runtime behavior and dependencies of that black box. Knowing how LaTeX chooses the bullet symbol for its list, for example. Suppose you wanted to change the bullet to some different glyph. You have to know what it's doing at runtime to get that and what dependencies it has on other data structures so that you can actually modify it if you want that in the future. Now, we've done a couple of studies of this. We found, for example, that we looked at 10 APIs and found lots of highly rated question and answer pairs on Stack Overflow and analyzed the content of the answers. And we found that 90% of the answers were composed of explanations of these three things: domain concepts, parameterized templates, and execution facts. That last 10%, they were things like comparing alternatives, clarifications to confusing language, and really just thank yous. So really the entirety of the content on Stack Overflow is one of these three types of things. And even more revealing is that most of the replies to answers were requests for further information of one of these three types. So somebody would say, I don't understand this concept, tell me what you mean by it. Or I need a different example to show this other related case and how it relates to the example you gave. Or I don't understand what happens at runtime when this occurs. Now, that first study established that this is important content. What is the effect of providing this content at different degrees? So we ran a between subjects experiment across 4 APIs. And we had several conditions. One where there was one of the three kinds of knowledge, concepts, templates, or facts. A condition where all three were provided, and a condition where none were provided. And we found many things. One is that learners requested these types of knowledge when they were not provided. So that's consistent with the prior study. Most of the tasks, the more of these three types of content the learner had, the more incorrect and complete their solution. But we did find that success depended highly on learners' ability to actually find the instruction on that content and successfully understand it. So that pattern of more content, more correct, was sort of confounded by whether or not the explanations of that content were actually good. So we're doing a lot of future work on API learning as well. We're building tools that automatically extract templates and facts so that learning materials can quickly adapt as an API evolves, right? So that designers could automatically generate some of these things. We're building tools for generating API tutorials automatically, where we can optimize the discovery and learning of API knowledge so that the instruction is actually good. And so we're really envisioning a world in which robustly learning an API is about careful reasoning about that API, not just about copy and paste on Stack Overflow, which leads to brittle programs, let alone brittle knowledge. So that was API knowledge, and the big idea here is that it's different than programming language knowledge. It's much more about concepts in the world, ways of composing things, and facts about those little black boxes inside of API functions. I want to move on now to something that's a little bit more cognitive and a lot less about the content of a language or an API, and that is self-regulation skills. So self-regulation is the ability to monitor your thoughts, your comprehension of things, the process that you're following, the decisions that you're making, the strategies that you're using. And so I'd mentioned before that Dostanai's work showed that programming requires self-regulation to make decisions about when to switch activities, when to seek new resources, when to try a new strategy, and so on. And what Dostanai's work has shown, along with other prior work, is that really strong self-regulation skills correlate very strongly with fewer defects, higher productivity, and better learning. And so this is something that we really want to understand. Is this a causal thing, and how do we promote it if so? How do we teach those self-regulation skills? So one of the first things that Dostanai did was tried an intervention to try to teach those skills. We ran a classroom experiment with 2 groups of 40 secondary school novice programming students. And what we did as they were learning and as they were working on their projects over the course of a 2-week class, when they asked for help, we did one of 2 things. In the control group, the teachers just provided help, like any teaching assistant might in a classroom. But in the treatment group, before we provided help, we asked them 3 questions. What are you doing? Why are you doing it? And is it helping? And the goal of these questions was to try to promote that self-awareness of their process, of their activities, of their decisions, and get them used to asking these questions of themselves. And what we found is that that's exactly what happened. That not only did they start asking those questions of themselves, they stopped asking us, and so they were more independent. And this independence led them to interrogate more on their process, which led to more productivity, and that productivity led to increased programming self-efficacy. So you can see some of our data on the right. This was the number of requirements that students had met. The lighter bars are the ones that we provided, and the darker bars are the requirements that students themselves had defined. So not only did they do more of the required ones, but they did more of the self-defined ones as well. This was just from this prompting intervention. So the big question from this work was, well, how do we scale some of this, right? What if you don't have a classroom with enough TAs to provide a lot of this prompting feedback? Well, we've shown that modeling self-regulation, even in a tool, can help as well. So this is the problem-solving tutor. It teaches self-regulation by showing examples of an expert self-regulating their programming. So this expert is this little smiley face guy. And I'll show you a quick example of it running here. Basically, you don't have to see the dialogue that's happening here, but the expert is talking about their process. They're talking about how they're thinking about the problem, how they're interpreting it, and you can see that as they proceed, there's a little title bar that goes from interpret to search to adapt to implement. This reinforces the fact that programming is a process and that each of these processes requires different activities. And so as this proceeds, this goes on and they start implementing the program, they get this checkerboard thing that they want, and all of this modeled behavior of self-regulation is something that we hope that learners will start to do themselves. And so we showed in a classroom experiment that providing this tutor before a programming project increased how much students self-regulated their thinking, and it also increased the difficulty of the problems that students chose to work on independently. It didn't change their actual success at those because the problems they chose were harder. Now again, just like with our programming language tutor, You might think this seems like a really simple environment. I don't understand what's so hard about this. This is sort of the classic criterion for computer science research. Well, there's a lot of hidden complexity in this as well. We had to invent an entire platform for authoring programming sessions in a structured way. We needed character-level revision histories, real-time visualizations of programming actions such as testing and debugging, self-regulation annotations on every action in the script. So we had to be able to link metadata to all of the choices that a developer was making and their modifications to a program. And then one of the hardest things was actually creating an authoring tool for writing these examples. Right? It turns out that writing a description of a process that somebody follows to construct a program is a very challenging task. And so Gus and I have been working a lot on tools for this. So a lot of our future work on self-regulation has been picked up. Many of these ideas are being integrated into Code.org's curriculum, just like our programming language work. This is being used by 10 million learners now. We're exploring new ways of measuring and teaching self-regulation skills at scale. We're exploring the many challenges to preparing teachers to model self-regulation and author problem-solving tutor worked examples. So really here we're moving towards a vision where every learner has strong self-regulation skills, and they're learning to do that by watching what an expert does. All right, so self-regulation skills. The big idea was modeling how to think about your thinking. Now this fourth and last topic I want to talk about is strategic knowledge. So let me tell you what I mean by strategic knowledge. Strong self-regulation skills really are useless if you have poor strategies for solving programming problems. It doesn't really matter that you know that you're struggling to debug if you don't have a good way of debugging something, for example. So how do we help people learn effective strategies for all of the different problems they might encounter in their programming process? So one thing we've tried is inventing a notation that explicitly represents expert strategies for solving problems. This is work that I've been doing with my collaborator Thomas Latoza at George Mason University. So here's an example of a roboto strategy. This is a program that a human executes, not a computer. And this particular strategy is for renaming a variable. So given some name in a program, the first step is to set this variable code lines to all of the lines in the source code that contain the word name. And for every one of those lines, if the line contains a valid reference, rename it. But then do the same in documentation. Find all the lines of documentation that contain the name, and for every one of those lines, if that line contains a reference to the name, rename it. Right? This is sort of context where rename refactoring might not work, like a dynamic programming language or doing search and replace in documentation. So the point of this strategy is not that somebody doesn't know how to do this process, although if a novice was trying to do it, they might not, but to help them do it systematically, so that they don't miss any steps and that they check every line and that they're keeping track of all of these details in some complete way. And the special insight here is that by writing all of these down, developers are just more likely to do all of these steps and do them systematically. So how do we ensure that they follow this process? Well, we have a little strategy tracker. And this tracker divides up responsibilities between the developer and the computer. So the person, their job is to make judgments about code, to gather information from the world, and to take action, right? Modify programs, change state, things like that. Whereas the computer's job is to ensure systematic work. And it does this by enforcing the steps of the strategy and storing the information that the developer has found. And so it behaves a lot like a debugger, but with reverse execution and fix and continue state editing. And so it's a lot like stepping through the execution of a program, but doing that as a guide to solving a problem. So one of the first studies that we did was to look at how does following one of these explicit strategies influence somebody's effectiveness relative to them choosing their own strategies. So we ran a controlled experiment with 28 developers that had varying expertise, and we gave them a test-driven development task and debugging task. In the control group, developers could choose their strategy independently. They didn't need to do anything in particular. And in the treatment group, we required them to use strategies that we provided. One, which was essentially a roboto strategy for test-driven development, and one was a debugging strategy that was adapted from some of my work on the Y-line debugging tool that I did in my dissertation work several years ago. And so what we found is that experts and novices that used explicit strategies were just more successful at both of these tasks. They designed more tests in the TDD case, and in the debugging case, they were almost uniform in finding the defect, whereas the other condition didn't find it at all. I think the most interesting finding here was that the more novice developers in our pool that used the strategies, that they were more effective at these tasks than the experts who didn't. And this says a lot. It actually says that the skills that are in somebody's head may actually not be as important as the strategy that they choose to follow for following a task. And that means that actually writing these strategies down and having people use them may be the biggest factor in whether or not somebody's successful at a task. We took that more expert study and tried to look at strategies in a more novice context. And so we went to a classroom of secondary school students. They were 20 adolescents, and we taught them a design and debugging strategy, simpler ones than the one that we taught the experts. And learners who used those strategies in the class were more productive and more independent. These were correlations, of course. So here's an example of one of these strategies. You can't quite read it, but basically it's a debugging process that says, brainstorm a bunch of the possible causes, check each of them systematically, and if you find one that is the cause, then find a way to fix it and stop it from happening. So a very simple process, but something that most of the novices wouldn't do independently if they didn't have this. So for those that were actually successful at using this and they were more productive, that was great. They said things like, they're like a formula for when you get stuck, or it forces us to actually look at our code instead of adding random stuff. But a lot of the other learners in the class, especially the ones who chose not to use it, they struggled to use it because they had weak self-regulation skills. They told us things like, I know it will help, but I just can't force myself to follow the steps. It's just so boring. I just want to change stuff, right? So a lot of it was their ability to control their behavior that was preventing them from getting value from these strategies. We've also done other work that embeds strategies inside of an IDE to make them even closer to the problem-solving work that somebody's doing. This is work I've done in collaboration with Margaret Burnett and many of her students at Oregon State. This is called the Idea Garden, and it puts a lot of hints about problem-solving in the IDE. And we have a whole series of studies that show that this results in improved productivity and independence. So there's a lot of exciting future work here. Just like with some of the other findings, we're partnering with code.org to write debugging strategies for a lot of their secondary education curriculum. We're exploring barriers to authoring strategies and learning strategies. And what we're trying to envision here is a world in which there are strategies for every problem that a programmer might encounter. So imagine a Stack Overflow-like site where you're searching not for some API knowledge, but you're searching for a strategy to solve a problem. How do I debug X, right? And then you get a strategy for how to debug X, and that makes you more effective. So these are these four bodies of work that we've done. They really cover the space of what programming is. So how do we teach programming given all of these things? Well, there are some basic implications for this that I'm willing to make claims about, even though we only have a few works for each of them. One is that programming is just not logic alone. It also requires planning, self-awareness, a lot of other sub-skills to be successful. All of these require some logical reasoning about program behavior, but they also require some systematic decision-making and process, and also learning along the way. So if we ignore a lot of these skills that are really essential to programming, we're sort of guaranteeing that most people who try to learn programming will fail unless they have really good self-regulation skills already. Now, we should also be just teaching those self-regulation skills explicitly. If they don't have them, they're not going to program well. If learners aren't aware of their process, their comprehension, and their decisions, they can't really improve them. So we need to be showing learners how to think about their thinking by showing them your thinking or using the problem-solving tutor when we release it. This is really essential. I don't think that we know exactly how to do this yet. We only had a few studies that show that a proof of concept that it works, but I think trying some of these things is really critical. And then to support all of those sub-skills, we need to teach strategic knowledge, right? Programming skill is hundreds of different strategies for solving hundreds of different problems. We should be teaching these strategies by writing them down and having learners practice them and teaching learners how to practice them effectively. And really, in some sense, this is no different than any other field of engineering, where there are entire handbooks that describe how to solve every known class of problems, for example, in mechanical engineering or civil engineering. The difference is that in computing and software engineering, we just don't write down how to solve problems. We just expect people to solve problems through their creativity, for example. And then finally, all of this fails unless somebody has a really robust ability to read a program's semantics and know how a program will execute. Right? We need to teach learners reading strategies and give them extensive practice on reading, or you might use the programming language tutor when we release it. We want to do this before we ask them to write programs so that they have a really robust understanding of semantics. And then, of course, if you're going to teach APIs, and many of you might in a class, it's easy to imagine that Stack Overflow and documentation is everything that a learner needs. It's really not. Most answers are missing key conceptual and semantic knowledge, and key information about the design space in which a code example sits, and how it might be adapted to achieve related behaviors. So we should be providing explicit instruction on API concepts and templates and execution facts to ensure that people are using APIs correctly. So one reaction that I often get to some of this work is there really time to teach all of these additional things? So here's how I think about that. Any teacher in any setting gets to choose one of two paths. You either cover all the material that you think is important, but you don't cover it well, and you essentially produce low-skilled programmers, right? This is what happens a lot in higher education, sometimes in primary and secondary education, is we, as teachers, try to focus on getting through everything rather than actually producing effective learning. The alternative, of course, is to develop really robust foundational skills and the ability to learn new skills, right? Giving learners the agency to learn those new skills, to produce high-skill programmers who are continuously learning, right? So which does the world really want, right? I think the obvious answer here is number two. This is what happens in workplaces when people are learning. This is what happens when people are learning as a hobby, right, or doing end-user programming. We just need to be doing this in formal education as well. So I've only done a little bit of work in this broader space, and there's a lot of other open questions, right? There's many skills around understanding problems, about searching for solutions, about analyzing algorithms that we really haven't talked about. And then, of course, this is just programming, right? There's a broader set of software engineering skills and more broadly computer science skills. Some of my new students, Alana Olson and Yim Register, are working on some of these, looking at things like data programming skills, machine learning skills, software design skills, algorithm design skills, data structure design skills. So there's a lot of work to do here, and the field of computing education research is just getting started. And then, of course, all of this has to be conditioned on the context in which somebody's learning, right? There are developmental constraints that make it so that some things in primary and secondary school don't make sense to teach. For example, our finding that a lot of the adolescents in our high school class didn't have the right self-regulation skills needed to use strategies. That might actually be a hard constraint. So teachers at different levels are going to have to teach differently, and the teachers themselves might have different expertise for that learning. And then finally, and I think most importantly, we have to understand how to make our learning contexts inclusive and equitable and diverse. If we don't, really few people will actually want to learn these skills, and the diversity of those people will be really low. And so this is what computing education research is doing. It's working on all of these problems, trying to help everyone succeed. I hope you can join us and try to contribute some of your expertise in doing this as well. Thank you very much.